Okay, good morning. So today I'm gonna try to code a neural network from scratch using Python, and so I won't be using PyTorch or TensorFlow and library like that. Though I will be using Pandas and NumPy for the math, and it's gonna be just a chill session. Not gonna rush it because I've done this before. I think in 2 courses in AI I know most of the math, but never really written the code from scratch before, so this is gonna be interesting. So we're gonna start off by entering VSL. Let's see here. It's just mkdir to make a directory. Not sure. Okay, let's call just. Oh, it was. Whoopla. That's not the right file extension. I'm gonna be lazy here. Just copy and paste. I don't know why. Okay. So, as mentioned, we're gonna need some stuff for the math, because this stream isn't about writing, like, what do you say? Or replacement code for NumPy or Pandas, so. Is it from NumPy? No, is it import NumPy as NP? And we're gonna need matplotlib, obviously. We're also gonna need pandas. So we're gonna run this, select environment, the recommended environment. I'm gonna zoom in for you guys. Okay. So for the data, I actually got some data here prepared. Let's see. We're gonna reveal this in File Explorer. So it's like a data set with some power plant data. Actually, I used it for one of the courses I just took. Okay, let's see. How did you read from that? Oh, come on. Yes. Okay. So use pandas to read the CSV file. That should be fine. Oh, oops. There we go. You can print out the top 5 rows. I'm not sure what these mean. Maybe the CSV file will tell us. No. Wow, this was not a very small amount of information to go on. I'm fairly sure these are the labels. We have the features and the labels. We're gonna split that up. So you write dataset dot underscore x, right? Can't we just type dataset all rows? I think you can write like that. Nope. Okay, let's see what happened here. Where did it go wrong? Invalid index error. Wait, what? 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 Why does it give us invalid index error? But if we now type just do the same thing there, we collect the attributes, we collect the labels, print out X, we want the shape of X. Okay, that looks about right. We also want the shape of the dataset Y. That also looks right. Can we type like print so we can print both of them here? Yeah, that worked. Okay. So let's see. How do we want to start? So we're just gonna install this extension to make the CSV file a bit more easy to read. So I'm gonna need paint to think a bit here. Or if I have any good pictures of this in presentation. I think I do. Hold up. I'm gonna look for a PDF file here somewhere. Let's see, where is it? I'm supposed to have a few presentation files here. Yeah, here we have it. Okay, so this is from the course I've been taking this summer, which shows us the like the basic mathematics of neural networks. So first, let's say we have our features, the inputs. These will be multiplied with weights in the first layer. And what is the layer, you might ask? Well, let me draw that for you. So, let's say we have the input layer. That means we have, let's say in this case, four values that will be inserted. So this will be called Oopla. So that's too thin. X1, X2, X3, X4. And together these make out like X. And let's see, this will be, yeah, we got X there. Poof. And this is what do you call when it's there's a T? It's transpose, I think. It's like when you flip it, basically. And these like inputs, these do you see neurons? These are basically the neurons. They all have a weight to them. So let's say 1, 2, 3, 4, and also a weight. I know this is confusing, but you'll soon understand what's going on here. Plus B4. Okay. Now let's say that we have our input layer here. And we will create a second layer that will be, let's say, just 2 neurons. Now what's going on is that these will be connected to each of the next neurons. Okay, let's make this one red like this. It's connected like that. That. Poof, like that. As you can see, it's kind of a mess. Whoa, whoa, whoa. Oh, this is hard. Ooh. Go like that. So, same thing here. We have a weight. Let's call this one, actually it should have a let's call it just weight 5 for now. This is the wrong naming, but sure, let's go with it. Plus B5 plus B6, and these two are connected to one last, which is the output layer. Poof. Which outputs the result. Let's call it Y. Take a look here if I see anything more of interest here. Yes. So if you look at this math here, so the output here is the transpose of the weights with dot product to X, the inputs, plus the biased. And so the bias is just something added to it. It's just a constant, basically. And this, let's see, I think this is the wait, let's scroll down. It's hard without all the notes. Okay, so I have the input layer, the hidden layer, the output layer. Yeah. Alright, the input layer doesn't add the weights and the bias. So in other words, this is kind of wrong. Let's we will remove this. Try again. Okay, so we have our inputs x1, x2, x3, x4. And we have our layer 1, which will be, let's say, 4. This looks like shit, but who cares? Yeah, so this is gonna be messy. Each input is gonna map to each neuron in the first layer. Oops. Wait. Okay. Wow. Yeah, something like that. Okay, so here we have the first weights. Let's so that's the first set of weights. I'm also gonna have the first call them bias. So these are connected to the first, layer. So this would be, yeah, this will be the first hidden layer, like the layer you don't really see ish. And let's say we want to create a second hidden layer. Now it's gonna be way less connections. Oh, that one's supposed to be black. Damn it. There we go. Okay, so we have our second layer here. Here we have the second set of weights and second set of bias. So this was thus the second hidden layer. Just to clarify, this one should be input layer. Wow, beautiful text on there. Oh, okay. Hidden layer 1. Hidden layer 2. And then lastly we have the output. Yeah, that's right. We do. Okay. And here there won't be 2 connections. And we add the last weights and bias. Okay, so this will give us our output. So, one more thing here is the linearity we have right now. So if you look at the math now for the output of the first hidden layer, we should have something like this. Let's call the values that comes out here A1, A2. So A1, hold on, get it. There we go. Okay, so A1 will simply be, scroll down, there we go, as first weights, and that's also transposed. So this is just to make the dot product work, like how we should flip the matrices to be able to do the dot product. I will show you later. So this is times the input, and we also add the weights. Oops. So this is the output of the first layer, but there is a problem here. As long as there's always an output, as long as we just do this linear calculation, we will only try to solve this in a linear way. So we need to break the linearity, and we do that using a activation function. So let's call the activation function G. So we're gonna wrap this inside G. Like that. And let's see, what will our next step be? Yeah. So the output of this would be a matrix right now. So somehow this can like be broken down to so for the first output here, A1, we take the first value. G, look at the weights, take first weight, the x, yeah, the x value, it's being given all the x values. Yeah, that's right. One. And this would continue same set activation function 1 2 transpose times dot product x plus e1 2 and so on. Beautiful. Okay, so we have the outputs from the hidden layers. Now, let's see. So the last calculation we would do would be y hat equals G the last weights, the T thingy there. We have A2, since our X now is the input here is A2 plus B3. So let's look at the let's look at this. This is great. So here we have an example. We have this simple network. Okay, so I have the simple network here to the left, and here we have the first layer, the first calculations. So Z, the Z value is the output based on the weights times the input plus the bias, and then the final output A is you plug in the Z value into the activation function, and you do this for all of them, all the neurons. And if we look at the math here, see, it's not really too complicated. Let's see. Yeah, so since there are 3 inputs, we know that this vector has 3 columns after it's been, is it transposed? I'm not sure. So multiply, let's say, wait, 1 1. All right, yeah. Maybe I shouldn't go into too deep here. Let's go back into Paint. Oh. I need more space for my drawing. There we go. Ah, beautiful. Oops. I'm not sure what I'm doing. Zoom in a bit more. No. Oh, damn it. Okay. Let's see. So, looking at this value here, this would be a matrix. Would it? Yeah. Of course, it's a matrix. It's could, for instance, look like this. Hold on, I'm gonna zoom in somehow. So V 1 1. This could be 1 2 3, meaning that the transposed version would be 1 2 3, like that. And this dot product with x1, x2, x3 would be x1 plus 2. Oh, I lost myself. 2 x2 plus 3 x3. And this is, as you saw, added together with West. This. I know I'm writing out the math in a horrible manner right now, but stick with me. So basically, these would be increased with some bias values. So yeah, that will give us the set values here. And lastly, let's see. Go back to the PDF file. So I have all the math here. Yeah, second layer would take the wait a minute. Yeah, we'll take the outputs that's been passed through the activation function, use that as inputs, and so on. So this number up here represents the layer. Visualization for multiple examples. Yeah, this is a good summarization. So here, the output value from one neuron. It's passed into its activation function. So this gives us the output. The output is then used as input for the next layer, said, and say superscript 2. And well, that output, this value is then used as the passed into the activation function, and this would give us the final output. Okay. Wait, what? I think something's wrong with the stream chat. Let's see. Now if I dive hi, let me your stream, but now can we connect on Discord? Sure. I will I'll send you a request later. Planner Kenny. Cool. I'll contact you later. Just gonna copy the name. Okay. So what else we got here? Blah 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 blah. Okay, so I think we might have enough knowledge now to start writing some code. So first of all, we know that the input is gonna be well, we're gonna have 4 inputs based on what we got here. And let's see, can you write classes in Python? Can you make objects? Oh, I haven't written enough Python in the last years. Let's see. So let's, can we define a class? Let's ask Copilot. Called input layer. I remember using classes. Oh yeah, you can. Cool. Okay, so we create an input layer class. On initialization, pass self as the first argument as usual. Take the input shape. Yeah, we're gonna need the input shape, obviously. And forward. Return inputs. Sure. Let's see if we can work with that. Okay, let's call it a second class can be called a hidden layer. You know what? Let's type some stuff here. Define layers. We're gonna input layer. Write some text here. Input layer. But the input layer also have weights and bias, so we're gonna have to creating a dedicated input layer is unnecessary. Though it adds to the clarity of the code. Could we just, you know, let's remove the input layer for now. So have a hidden layer. and we have a shape. Wow, okay. So we're gonna have to create the weights. From the beginning, we don't know the weights yet. As if we look at the calculations here, we see that we're using some weights and bias, and these are values we're gonna calculate later. But to get started, you can just add random values, because at the beginning, before the training of the network, it has no idea how to do the work correctly. So let's some weights. Okay, so we're gonna create a yes, numpy array. We're gonna create random n, rand n, some input. Okay, so as input shape is gonna be in this case this. Gonna be 9568 times 4. Doing this will give us an array that is just like this. It's a one-dimensional array that goes on until, let's say it starts at 1, just counts upwards. It would lead us to 9568. Oops. So I created the weights. We're also gonna have to create the bias, and the bias should be the same shape. So wait. Something's off here. Something is off. Hold on, I gotta check the math here. Math do be mathing. Wait. Should we maybe define a neuron first? Or is that redundant? I have to think. So take the poof. Wait. Let's create a neuron. Just 4 values, yeah, that's about right. So bias should just be n self input shape. Wait, should we have more? So the shape that we'll take is just 4, sorry. Four is the shape. Then we have more creates, because right now here we only create like oops, I destroyed that. If we start F1 we would just create now. This isn't enough, it has to be two-dimensional. We could create a class for the neurons. That, I mean, why not? It would slow down the code, but it would clarify a lot of stuff. So, input shape, put underscore shape, input shape. And it would have, yes. So I know it suggests something else here compared to here. I think this is maximum value. What is the second argument? Samples from the standard distribution. If possible. But let's be lazy and just run some code. Okay, yeah, I see what's going on here. We're gonna go with, since we're gonna rewrite this, let's ignore it. So if we do not type 1, it won't be nested. What happens if we type 0? Okay, what happens if we type 2? Oh, it's two-dimensional! What the shit? Okay, that means we can just fuck the neuron class. And if type 4 there, this will give us, for instance, so we have a two-dimensional array here with all the weights we want. Okay, okay. So we have the weights, and oh, you know what? We're gonna look like that. Can we simplify this somehow? It would be neat if we didn't have to write it twice. Yeah, I couldn't simplify it. So we have that. So we don't really have to pass an array. Let's just pass the hidden layer a or let's not call it hidden. Let's just call it a layer. That's fine. An input shape should just be an integer. Is that bad? But it is written to be one-dimensional right now. You know what? Let's pass it an array. Fine, fine. Then bias is gonna be self.input blah blah blah. Wait, what am I doing now? Yeah, I guess that's right. So we're basically preparing to handle multiple channels, which isn't the goal with this, but it might be nice to have it here just in case. Okay, let's just gonna check my chat here. Another chat. Okay, sorry about that. So I got the question here. Like, I'm gonna show you. It's better I show you. So this, like, what is a neural network, and like where does it belong on this chart? So a neural network belongs in deep learning. So basically, artificial intelligence itself, well, as you can say here, it's a program that can sense through reason, act, and adapt. But when you say artificial intelligence, you often think about, you know, like robots that can think, like just AI, you know, like humans made of computers. And inside that we have machine learning, which is what we basically use today. And more specifically, it's deep learning. So it's when we add multiple layers. Imagine, like, it's basically when we add so much math to it that we don't really understand what's going on anymore. That's how I like to describe it. It's like most people seem to understand it when you say it like that. Okay, so let's go back here. So far we have the we have started a layer here. So my monitor is acting up here. There we go. So we have something's going on with my audio. I'm gonna have to reconnect my headphones. Can you hear me? Yeah, okay. So I have weights with bias now. I'm gonna have to perform the calculation. So we have inputs. So the inputs are gonna be multiplied. Let's see, how do we do this? Yeah, we're gonna have to use the dot product. No, for dot product, yeah. We take the weights and the inputs plus bias. Yeah, this is correct. Okay, so what do we here? This row. It is the same as. Hold on. I'm gonna bring up the PDF again. Okay, something's happening. Okay, let's try again. So this math we see here is the weights, dot products to the inputs. That's this, plus the bias, B. So we can rename forward to like calculate Z, just to know how these are connected. And now that we've done that, let's see. Will this work? Should work. Does this transpose it? Let's run a few tests here. Okay, so let's call layer equals for 1. Okay, so now create a layer with the shape for 1. Yeah. And with that, let's print out the weights. Let's add so get the weights. We can get the bias. Yeah, that looks decent. And then we will, what will we do? What will we do? Yeah, right, we will just type layer, calculate, and let's give it a just this as input. So that this means that we're gonna multiply just a bunch of zeros and then add the bias. So what we should end up with as output is a one-dimensional array with just the bias values. No, that was not the case. Wait. No, of course not, of course not. I have to rethink this. Take the weights. Wait, why is the... Yeah. Why do we receive... Should we receive a just one-dimensional one? Oh, yeah, this is what's happening here. These are just the weights, the bias, repeated over and over again. That's odd. What is that? Oh, okay. It's because of this the shape, I think. Okay, so let's be lazy for now and just skip this. So now the bias should be just a one-dimensional array. Yeah, and the output is 1, 2. Okay. This is correct. So we created a layer, done that math. So next step is to break the linearity. And we do that through an activation function. Okay, so if we look here, is this a good image? Yeah. These are some of the activation functions. I think there's more activation functions, but let's see, someone that you've heard about. So the sigmoid function, this one's pretty common. Well, it was common. And tan as well, I think. But nowadays you mostly use this one. Really. And well, this is what it does. Basically, if it's 0 or less, it will just be ignored. So if the output of a neuron is error 0 below, it will just be poof, destroyed, removed, basically. And the formula for this is super simple. Yes. So basically, I think we just take the maximum value that we find, but the lowest value can be 0. So if we define one more function here, def relu. Wait. Okay, so NumPy has a maximum function. The real element is compared if Um, the arrays holding the elements to be compared. If that shape is not shape, blah blah blah. Okay. Oh, there's more. Oh. Okay, okay. Oh, examples. Okay, so give it to arrays here. And we return, pick the largest values at each index. So basically the order doesn't matter. Let's give this a try. Just type print numpy maximum, let's say 5 and 0. This should return 5, but so should this. Yeah, okay, okay. And so now that we have our activation function, you know what, let's make it so we can pass the activation function. Or select it activation function. This activation function, activation function. Oh, not this, damn it. Wrong language. Okay. We're gonna define, calculate we're gonna self and inputs. Can we type it? Make a switcher? You know what? Can we pass a function to this? So let's say we define. Can we create static classes? No, the field's unnecessary. Or is it? Should we keep the activation function inside the class, inside the layer class, or not? I don't know. I can't decide. Let's do that for now, maybe. Yeah, let's do it for now. We'll create a switch. Wait, was it case? Okay, so first we create calculate set value, and if you know what, no, let's create a static class. Let's do that. How to create a static class in Python? Create a class with the static function really. I don't think you can do that in Python. Can you? Static method. Oh, static method. Oh. Okay, yeah. Okay, so we can remove that and return self activation function. Yeah. So now we could add a few like checkers. So if let's say activation function is null. No. Oh my god, how do you check if a value is null in Python? Okay, let's just cheat again. If input shape is null. Okay, something's... Oh my god. Something's going on with my monitors. I have to turn off this program. So I have Space Desk to use my tablet as an external monitor, but it keeps connecting and disconnecting, even though it shouldn't even connect right now. Okay, there we go. It's probably fine now. Can't promise anything. Yeah, so if it's none. Oh, if it's none. Oh crap. Okay. So if input shape is none, raise value error. Yeah. Okay, that looks right. Do the checks. That's real simple checks. Just we're still missing a lot of checks here. For instance, we need to check that the shape of the input shape, that the activation function exists, and so on. What the hell is going on with my monitor? Ugh. Let's see if I have a function running in the background. Well, this is not going great right now. Okay. This is crap. Can turn off Space Desk. Okay, hopefully that will help. Hopefully. So we have a layer here. Save that. So this should give us an error. Type error. Okay, so it's missing activation function. Activation function is not defined. Okay. Oh. I hadn't run the block, so it didn't exist yet, so now it should work. But we're still getting an error. What do you mean it's not defined? It's okay. This looks great. Oh. So now we have a way to create layers. So this input shape. Let's try to connect layers. So first we have one layer here. Let's call it input layer. And let's do some printing here. They created the input shape. Save that, run that. Okay. Okay, so shape and maybe we can create an array instead. Does this work? So create a model here, give 2 layers, and those are not like connected now. Okay, so this would be the shape. So I have dataset X shape. Now it's gonna take in input like this. Dataset X shape 1. Shape. Okay, so that's how I get the input shape. So we take the second value inside dataset X shape, which is 4, and then tell it's going to be one-dimensional. Give it the activation function relu, and what do we do next? We will this is interesting lo-fi. Let's create a class called model. Oh, look at this. Okay, so we yeah. So upon the construction, we just create an empty array right now with the layers, but this is kind of lazy. So you're gonna allow it to add the layers from the beginning. So for each layer inside layers, we add the layer using the defined add function here. We just append the layer. However, I think this is, we're not gonna add the predict yet. Let's ignore that one. So add the layers. Let's here. Model equals model. So create a new model, and so the output of the first layer, what will that look like? So this should give us the oh, not predict. Calculate a wait. what is wrong here? Just the roof. What? Truth value of an array with more than one element is ambitious. Use any. Oh yeah, of course. So we pass this an array. So we're gonna have to. You know, let's flip this. So we have x and then x dot. We have to create a array of just zeros, so it has the same shape as x. And there's a way to do it in NumPy zeros, like that, I think. So what this does is that we tell it to create an array full of just zeros of that size, as you can see here. So we save that, and this should work now. No, it did not work now. Maybe that wasn't the problem. So return max, blah 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 blah. Okay, so that gives us that value. One-dimensional array. Calculate A. Get the error. Wait. I think I just got a spam in my chat. Cool. Second spam today. Or is it not spam? Best viewers on. I have no idea what that URL is in the chat. I will not click on that. Will I? No! No, I have to resist. Best viewers, let's ask. Not sure I should click. Okay. Oh, I can't just reply. Hold on, I gotta sign into the chat. Let's see. Wow. Wait, now the chat worked. When I wrote in the chat, it worked. What? What? What's going on? Okay, let's just continue. I noticed, by the way, that wrong monitor is primary monitor right now, so I'm gonna change my settings here. There we go. To give a bit more space. Okay, so let's get back to this. So I had an issue here. The truth value of an array with more than one element is ambitious. It's ambitious, okay. So I think we have to split up the calculation. This is just maximum, it's not numpy. Now. There we go. So the problem there was I was just using the max function, which doesn't support vectors. And well, since we're building a neural network, we need vectors and matrices. Yeah. Back on track. Yeah, as we can see. So if we look at the output here, see we have 0, 0, 0, which implies that. But these are negative ones. Wait, oh right, yeah. So this is just calculating the Z value, and we have the A value. Since this is negative, negative, positive, negative, we know that it's going to set the negative ones to 0, and the positive is going to remain the same. So by doing this, we're broken the linearity. Let's scroll down and look at the model. We add all the layers given in the array. We can also add more layers later on. And the input shape, well, that will be the shape of the layer. Why do you call it input shape and not shape? I think that's better. Wait. Subtle shape. There we go. We can just use the shape here, not self.shape, since it's shorter. There we go. We're gonna save this. It's working. We know that's still working. So looking at the drawing here, let's say we define, I want to have both of them visible at the same time. Okay, perfect, you can see most of it. We create the first layer here, and we know the shape of it. It's 4 times 1. Second one will have 2 now, so let's actually go with, yeah, let's go with this. Perfect. So second layer we add here with this layer. hidden layer 2. Or should we just go with an identical one? Wait, so the input layer only takes the inputs, it doesn't really do anything to it. So I guess we do have to add a input layer class. So you're gonna rename layer to hidden layer. Also rename all the code used for debugging, all the variables. Hidden underscore layer. Then we're also gonna have to create the class input layer. Gonna define init to itself. There we're gonna have to what we'll do here. We're gonna take the shape. Wait. Can't we just take the input shape here? Yeah, okay, so input shape. And we don't need an activation function. So we're gonna store that input shape. The input shape will if we give it this as input shape, we don't only have to look at that one. So basically like that, I think. So we'll select the first column and yeah, we'll ignore the first column, like the first value, and just take the rest. I think that should do it. Let's you suggest an output shape. Why do you suggest an output shape? Why would we use that? Input layer. Shape. Can rename this hidden layer. Okay. Input layer. No activation function. Oops. I don't think I run that one. Yeah, I didn't run the cell. No. Model is not defined. What do you mean model is not defined? Okay. Hidden layer is not defined. What do you mean it's not defined? Did I make a typo? Okay. So this is obviously wrong. The shape is not 1. Maybe? Nope. Let's solve this elsewhere. Okay, that was select the first one. Actually, I think we just need to grab that one. So just type 1. So we have the shape of it, and that shape just 1. That's good enough. Should we put that inside an array? Maybe? I don't know. Yeah, let's put that. No, let's leave it like that. Wait. Shape 1? What do you mean shape is 1? Four. input layer, input shape. What's going on here? Input layer. Oh, yeah, we can just pass it the shape of that. Okay. Is that wrong? I think it is. We'll scroll up, we will save just the input shape, that should be enough. Okay, so we have the input now. Shape 4. And the outputs of it, if you tell the output of it, the output of that one should be, wait, do you need the output of it? I think we do. I think we do. Yeah. So if we were to calculate A1, we would use this math, right? And by this math, I mean this math. And so the weights, he'll tell it the shape of this is kinda necessary, because it can just pass down from input layer. What we could add here though is the shape of number of neurons. So we'll continue building this model as in Paint. Yeah. We go to the hidden layer. Shape should be renamed then to neurons. Go. We run all the cells. Okay, so wait. 2 blah 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 blah. Oh. Let's call it 4. Wait, what? Int object is not subscriptable. The fuck? Bias. Oh. There we go. We have the number of neurons. And the shape of this, yes, it's 4, 2. That's good. I think we can add one more here, then it's just like 1, which would be the output layer. If it's just 1, it should be called output layer. Yeah, let's if neurons equals 1, output hidden layer, else into the layer. I think this will clarify a bit for us. Yeah, okay, so we have the input layer, shape 4, hidden layers, hidden layer, output slash hidden layer, neuron 1. So we would give 4 attributes and get one label, or just one value. But how? Okay, so this one. Take the for to predict. Let's see what it suggests here. Predict. So take the inputs for each layer. We'll calculate A. I think it's time for me to take a break soon to cook some lunch, to be honest. Let's see if we can finish this first. So, we give the input layer its values. You know, let's rename calculate A to let's call it forward. Calculate Z to weights and bias. Where's that? That is kind of unclear. I don't like that. We're gonna keep calculate Z. Not sure about calculate A though. Oh crap. Because first layer doesn't have it, the input layer. But do we need to use the input layer? If it's an input layer, okay, then we just skip it. Yeah, that makes sense. Oh crap. Okay, so since the input layer doesn't have any weights and bias, we can just ignore it, and we'll continue to the next layer, which will be the first hidden layer with 4 neurons in this case. We do the math there, we get the output. And the output, we're gonna have to do this an example calculation step by step to see how this works. But for now, I'm gonna have to take a break to cook some lunch and eat it. So I will see you soon. So I'm back, but I brought some lunch. I thought it would be nice to watch some videos while I eat it. Obviously about neural networks. With mic off, so you don't have to hear me chewing the food. Let's see. I'm gonna find a clean Chrome window. I was thinking about 3 blue, 1 brown. If you haven't checked this channel out before, you should do it after this, because it's an amazing channel. Let's see, I'm gonna turn off the music a while. There we go.
As a 3. And I want you to take a moment to appreciate.
So here you're gonna see most of the math I've shown so far, and probably some more to it, and it will probably help you understand what I'm really doing here.
How crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to... well, the task goes from...
So what's going on here is that this is not just a basic artificial neural network. This is a CNN, which is what we use today to classify images. But it's still pretty much the same thing, because if we take each row in this matrix and place them like on a single row, just we flatten them out, then suddenly we can treat this as just a normal equation, basically.
From comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel. ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, lit up when its activation is a high number.
Okay, so activation, that's the activation function I was talking about earlier, where I was using ReLU.
So all of these 784 neurons make up the
flattening
first layer of our network.
Like that.
Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1.
So here we have the math. We did just do the matrix multiplication with not matrix multiplication, dot product between the weights and the inputs, and now we're passing that into the activation function, in this case sigmoid.
And it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on.
Okay, so sorry for pausing the video there. I just wanted to say that I am done with eating lunch, and let's finish this video because it's interesting to see, and also it helps a bit to understand what's going on right now with the programming.
And the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active.
Hi, by the way.
And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases, 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand.
So I don't know if you've done linear algebra before, but like if you have, you know that, for instance, matrix multiplication is a pain in the ass because it takes so much calculation. It's so tedious, and this, if you were to do this by hand, I mean, it would take so long.
Purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when...
I mean, what he's talking about here about calculating it and keeping track of it, not treating it as a black box, I mean, it's a good idea, but then you also have to keep the problem very small. So he's working on like drawn digits in this case, 0 to 9. And they are a bit too high resolution for you as a human to be able to perform these calculations in a reasonable time frame. So if you were to do it on images with lower resolution, like 8 times 8.
When the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions.
I need to find the best way to learn math and science.
It's brilliant.org.
By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it.
Again, here we have it. We have the weights multiplied by the inputs, and we have the bias, and put that into the activation function, which in this case is the sigmoid.
If you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes...
So I think we're gonna end the video here and get back to the code. So what I have so far is the following. We have data sets stored in a CSV file. We looked at the top 5 entries of it, and here you see that we have 5 attributes, 1 label. Well, do you call it label? I'm not sure. Well, this is basically the output, and these are the inputs. So we want to create a model that can predict PE based on these 4. So we separate all of them, so we get the attributes, the outputs, and print them out to see that we have this shape. So we have 9,568 data rows. Do you say? Yeah, I don't know what you say. How do you call it? And he just did some experiments with creating randomized matrices, because this is used for creating the starting point for the neural networks, neurons, weights, and biases. So if you look here we have 2-dimensional array where each array here represents what do you say, the weight for one neuron. So first neuron, second neuron, third neuron, and fourth neuron. Then we have an activation function. We use ReLU, which is super simple. Basically, if it's below 0, it will be just equal to 0. We create the input layer. We have create a hidden layer. We will also create an output layer. So let's add that now. Oops, output layer. So this makes sense. So it will take one argument here, output shape. But there's something missing here, the activation function for the output layer. Let's see. So we store the desired output shape and the activation function. We print out that we have created an output layer. Let's add that to second line. Def calculate, not output, calculate. Yeah, maybe calculate output. Maybe that's good. It's pretty clear. It's not the cleanest code, but it's clear code. So we'll save that. Scroll down. Here we have a class for the model, and here we're gonna replace this to output layer. Okay, so we have an input layer, we have hidden layers, output layer. We also have to modify this because I prepared the hidden layers to be output layers too, but that is not the case anymore. Okay, so we will run all the cells again, and we see that it seems to be working. So if we were to run this now, let's say we start with the input layer. Okay, let's create an input, and it will be just a bunch of zeros. We write res as a result. We pass this. Oh, we have to let's type model dot layers. So for the input layer, we're just going to pass the values forward. As you can see, we do here, because the input layer doesn't really do anything right now. But maybe the input layer should have an activation function. Let's do a quick Google search. Neural network input layer. You know what? Let's go with TensorFlow. Maybe they can tell us. So I have the input layer. Oh, it's horrible weather outside. We have the same batch size, sparse input tensor name. There's no like activation function here, so I guess we will skip that too. Which means this is unnecessary. And this will be a 1. Print A1. Okay, so the output of A1 is this. Meaning that the first and last were 0 or negative. 8. Oh wow, it is bad weather outside, so I got distracted by the wind. Okay. Then we print out A2. Okay, here we have a error. That's great. So let's see the problem here. We gave the second layer an input of this shape. And when we do that, let's scroll up. So there's a typo there. Just typo, blah blah. There we go. We create 4 neurons. The neurons. Okay, so I see the problem. So the problem here is that we assume a shape for the input based on the amount of neurons. That's wrong. So we can. Let's see. So if that one's 4, we know that the input of that one's gonna be. Wait, 4 is gonna go 2. Of neurons. So I think we're gonna have to modify these. So let's see. If the length oh, this is a pretty good check to add. I know what, let's not add that. Okay, so if the length is greater than 1, then self.layer, yeah, plural, take the last one, dot input shape is equal to the neurons of the layer before. Now let's type like this so it's clearer. So what to do here is that we have inserted a layer, and when we add, we check if we have 2 or more layers already added to the array. When we have, we will start adjusting the input shape of the newly added layers. This is required really, because we need to have a proper sizes of the matrices. So we're gonna inside hidden layer we will. Can we just define it empty here? Input shape none. There we go. Because this will be set from the model class. Okay. But when that is set, oh, okay, we're gonna have to create a function for this. That's better. Def set input shape. Okay. So yeah, here we're actually gonna set the weights bias here. We don't need to print this out for now. Yeah, maybe we won't print it out. So the weights will be the neurons times the input shape, and the bias will be the neurons, which we already knew. We already knew the bias, so we don't need to set that here. The weights though needs to be set, but since we're doing that there, we might as well just everything there. Set the input shape. You just set the neurons activation function. Let's make this a bit more neat. There we go. We don't have to define that one there. So we will call upon set input shape from the model class. we go. I probably broke something. Yes, I did. Yeah, we can't perform the calculations now. So we're gonna comment that one out. Running fine, running fine. Okay, here we have a problem. Input layer, object has no attribute neurons. Nope, that is true. So if that one is none, then we will just set this one to oh, I was thrown away. I'm not sure where I am anymore. There we go. This one will be self the layers. We go back to from the end and input shape. So we just copy the input shape. And we still get an error here. Input layer object has no attribute neurons. Okay. Wait, what? So it's 2. Wait, 2 doesn't matter. It has to be 3 or more. Oh, now it should work. What? Output layer object has no attribute set input shape. So the output layer also needs to set input shape, I guess. Can we create a interface for the layer? Create an interface for called layer. Let's see if Copilot can handle this request. ABC. Oh, it was an abstract I was thinking of. Okay. So we create an abstract class here. Okay. See, here is from ABC. And we will copy this here. This will use the layer abstract class. It's running fine. We can remove that one. That's redundant. Like so. We continue further down. Okay, can't instantiate abstract class hidden layer with abstract method set input shape. Okay. Can't instantiate abstract class. Wait. With abstract method. Google to the rescue. Python abstract class. Not function. Abstract classes. So we need to import that abstract method. We use that. Triangle, blah blah. No sides. Yeah, so that it looks like I'm doing this correct. Oh, you know what? I forgot about the music. I'm so sorry. There we go. Now it's cozy. Okay, look at this. Can't instantiate abstract class hidden layer with abstract method set input. Okay. Yeah, but I don't want to implement the set input shape into hidden layer. That's not what I want to do. Let's... Should we instead... Does that work? Can't instantiate abstract class hidden layer with abstract method set input shape. Why not? Instantiate it. Can't instantiate abstract class. Wait. This is confusing. Can't instantiate abstract class hidden layer. Set input shape. Okay. It's abstract. It's not the. It's not an interface. Okay. Of course, yeah. Okay. Maybe it can extend the class. Can I extend to just type layer? Is that enough? Oh. It was? Cool. Okay. Perfect. Output layer has an attribute set input shape. Yeah, sure, but it does now. Does it? Yeah, but it doesn't have neurons. So output layer. That's output shape. So if we have neurons, let's keep calling them neurons. Where do we get now? Oh, it is working. It is working. What? Okay, so the input shape for that one's 4, that one's 2. Wait. It would be nice if they were giving names. We're gonna be giving them names. Input layer. Should the input layer be given a name? No, it can't just be called input layer. But should we name it here? Tricky. Where should we name the layers? When we add them? Yeah, of course we're gonna name them when we add them, but the question is, should we name them based on the type? That would be nice. Can we select the type of this layer? Yes, we can. We also want to add underscore here to make it more readable. And we'll have to make sure that all the layers, no matter the type, have that they have this, the name. Wait, do we need to do that? Maybe it doesn't have to be defined. Let's remove that. So add them. We print out some information about each layer we add here when we initialize them. But we initialize them before we add them to the list. So I think we can remove this for now. That one too. We'll scroll down. And this is where we'll print out that we've added the layer. Added layer.name. Let's see. With input shape, yes. Can we write We could append it afterwards instead. So move like so. This can just be layer. And this one will be decreased to -1, 2, 1, 1 maybe. Let's at least do it in that order. I totally broke something now. Yeah, I did. Cannot concatenate string, not int, blah blah blah. Oh. Just type error. Okay, no. Apparently not, I was wrong. Again. Hidden layer has no attribute input shape. I thought they did. Set input shape. Hidden layer will have that. Hidden layer has no attribute. Okay. Input shape. How come it doesn't have it? So we added the new layer. Well, let's comment this out first. See what happens. Okay, so we've added those hidden layer. Okay, so we're still printing out something somewhere. Yeah, here we're still printing. I wanna remove that. Solve this. We see that hidden layer for some reason doesn't have input shape here, but we are calling upon the set input shape unless this is incorrect. Okay, so if it's equal to or greater, then we set the input shape. But we won't set the input shape on the first. Well, I'm just I don't know. Input layer has no attribute neurons. No, it does not. I think I lost myself in my own code. So if it is equal to 1, we'll look at the last one. Oh no, it cannot be 1. If it's 2, we have 2 layers. 1, 2. Then this shape, the input shape of that one is based on that one. Meaning we go to the input shape again. And we see it has input shape. Could call like get output shape. Let's create a function here. And if we have if neurons is none, so if neurons is defined, shape is defined. Wait. It's hiding the code from me. But okay, what if you just type if self neurons? It's not none. Okay. Else. Okay. That's good. So now, instead of looking at the input shape, we just ask it what is the output shape. Well, instead of looking at input shape or neurons, depending on what the layer type, we just ask it and we'll know. So basically we move the logic here. So all layers will extend layer. So if it's equal to 1 or greater, remove this, call, we set the new layer being added, we set the input shape of the new layer being added based on the last old layer's output shape. So input shape should be the previous layer's output shape, I guess. Okay, then what? Empty. So add it, we append it. Input layer already has to attribute neurons. If it's not. Yeah, but I wanted to check if it has neurons, okay? What about that? Is that how you do it in Python? That is not how you do it in Python. Okay, I bet it is like has attribute or something like that. That's that wouldn't be impossible. It would be reasonable. If self has the attribute neurons. Let's see what. Okay, it has attributes. It's like JavaScript. Scroll down. Okay. So we added an input layer with input shape 4. We added a hidden layer with input shape 4. One more hidden layer input shape 4 and output layer with input shape 2. And oh, thank you so much for following. So we know the input shapes of each of them. So if you look at paint, at my beautiful drawing, it's beautiful, right? So let's actually move it a bit to the left. So we see here that the first input layer has input size of 4. The hidden layer, first hidden layer, called hidden layer 2, has input shape of 4. Wait, so we're passing 4 there, input shape of... Oh, okay, so this, yeah, right, this is the shape for each neuron. So we need to oh, hello, free cakes. Free cakes, nice, great username. Let's see, what do we do? So we have the shapes of the input size of each neuron. Should maybe also print out the full size, so also the amount of rows. in this matrix? I think so. I think so. We will look at. We added this input shape. Should we also get the neurons? Where do we set them? Let's go to. Hello, hello. Okay, hold on. I just gotta refill this water bottle. I am back, and I brought water. Okay. So where were I? Or where was I? We have the shape of the input there. There's X. Oh, damn. My brain is shutting down. This is just gonna get more interesting from now on. Let's see. We have the correct shapes, you know. Let's print out some information about the layers it have added for us. Layers. Let's look at the first one. That one should be called input layer 1. That's good. If we look at the input shape of that one, it's 4. Look at the second layer, which is the first hidden layer. This should cause an error. Wait, it doesn't? It has an input shape? Oh my god, what have I written? Yeah, I guess it does thanks to this class, yeah. It's gonna look at weights instead. Yeah, weights shape. Okay. That's correct. Let's see. So we have the shape there. We could print this weight shape. This input shape. Okay. You know what? Let's see what happens when we run this. Okay, okay. Here we perform like a the calculations it will do during the prediction, during the forward propagation, as it's called. But we do like step by step with just code to see how the values change based on the input that's just a bunch of zeros. So if I were to regenerate the model here, we would get a different output here. Yeah. That's because the weights and the biases are randomized right now, the initial ones. So I think if we were to perform prediction, it would spit out a value. Yeah, almost. Okay, so we can't call this function calculate A, because then we have to target different functions based on the type of layer. So I suggest we just go with just forward as name. since we are going to move forward in the propagation in the model. We basically go. We have the model here. We just go this way, right? So layer by layer. Oh, crap! That's replace all of those. Wait. What did I do? Forward. Let's remove that. Forward. So we have that for hidden layer. Maybe use it for output layer as well. You know what? Let's do it for layer also. No. So when we send the inputs into the layer. Oh my god, no, not layer. Input layer. There we go. Okay, so we have the input layer here. And the input layer doesn't add any weights or bias, so it's just gonna pass it through. So now when we go down here, let's see. Predict. Yeah, we can remove this is instance function because we don't really care if it's an input layer, since with the input layer we'll just pass input forward. It won't do any changes to it. And okay, so it gave us this. So I was hoping for an output shape of just one value, but I guess this will do. Okay, if we need to solve this prediction somehow. Let's explore this layer, see what it looks like. So model.layers. We select the last one. Weights. Okay, so I have 2 weights here. Let's I guess it makes sense. We look at the drawing here. Okay, so input layer, the hidden layer, the second hidden layer, and the output layer. So the output layer have 2 weights. But what is the output of this layer? I would like to know that. Let's do a calculation with it. Model layer minus 2. We can actually call by. Okay, so we know that this hidden layer have 2 neurons. That's good. So it should output 2 values when we do a calculation. Let's call forward function with yeah, let's just go a bunch of zeros. And we got 2 outputs. These are 2 outputs. These 2 values, or the integers, should be then combined to 1 in the output layer. Should be, theoretically, that's goal, but we'll solve that somehow. Okay, so model dot layers minus 1 weights. That should be 2, yeah. But the outputs. We're gonna print out some information about the last layer. The output layer. and it's only one bias. So right, wait, what's happening? What is happening? I need to look at the math. Okay, we're gonna do some drawings down here. Let's do it. Okay, so we know that okay. So let's call it V4. This one's equal to 0.66, 2.29. Let's call it 0.66 then, and 0.29. I'm so horrible at this. I'm sorry about the handwriting. I know it's hard to read. Oh, but maybe it's not hard to read, but it hurts my eyes to see it. And we have a bias before, which is equal to 0.08. So when we take W4 with T, when you flip it, multiply that by an input, let's call it X, plus B4, we should get something that is just a single value, unless there is an error in the hidden layer calculation. Okay, look at 4. Let's double check the name here so that we know we are looking at the right layer. Hidden layer 3. Yes, it is the right layer. Ah, damn it. Scroll back up to, okay, so to call forward here, calculate Z. Let's print out Z. So this is probably, wait, that is Z, I guess. Wait, is it? Yeah, it is. So we see that the activation function removed the first value. I think the error has something to do with this. Could be. It's a it is a two-dimensional array. Yeah. Okay. The name. Forward here. Name of the weights. We're looking at this layer. Since both of them have 4, so each row here in this array belongs to one neuron. And it would get the input shape should be 4. Yes, it is. So the output will be 2. As we get the 2 outputs here. That's correct. So if you look at the last layer again, it gets 2 inputs. Okay, we go to output layer. We have the input data. I will just call upon activation function. Wait a minute. That's not right. Wait, I don't even perform a... We don't calculate set. We have... Wait, we don't have weights? Did I just start this class and then finished it? Let's... Wait, I think I add the weights... Yeah, I add the weights elsewhere. I add the weights... Yeah, where do I add the weights? I do that... Here. Yes, we do have the weights. Let's copy this to output layer. Maybe? Yes! Yes! Ha! We have one output, look here. Here it is. Okay, so let's clean this up a bit. We can remove that, remove that, remove that. Let's run again, just that feels good. Okay. Can remove that line. Necessary debugging, let's fuck that. That's just trash now. Okay, this was just for testing. Let's remove that too. Okay, so we know that the calculate Z function here is it's just a dot product, and we add the bias. So we can move this to the base layer class, so you don't have to write it twice. And remove it from that one too. Okay, should still be working fine. There we go. We're also getting some weird outputs here. Yeah. Yes. Yes. Ah, finally. That took way longer than I thought. Okay, so let's go through the code. We import the libraries we're using. We use NumPy, Pandas, Matplotlib. Haven't yet been implemented, but it will probably be used later. We import the CSV file. We explore the first 5 rows. Then we separate the labels from the attributes. We print out the shape of each, just double check. Then we define activation functions, and since we're only using ReLU, that's the only one we will be activating. Furthermore, we define a base layer. Let's call this base layer class, used to extend other layers. Note that some of the functions methods, sorry, it's methods since it's in class, in this class are not used, or they're not used and not fully supported in all types of layers. Okay. So get output shape. Get the output shape of the layer. Basically, it's just we added it there so we could just move the logic elsewhere, which is cleaner. Calculate said the output of the layer without the activation function. So here we haven't applied the activation function yet. And okay, so we look at the input layer. The input layer is super basic. That's just like, oh, we get the shape of the inputs, and when we start for propagation, we literally just pass it through. We don't apply any weights or bias. So let's type that just because we can. Input layer where no weights, biases or activation functions are applied. Perfect. Then we have the output layer. I know it's a bit weird order right now because we can skip the hidden layers here, but it's the next layer we'll talk about. Okay, so we have the output layer. We say the amount of neurons we wanted to have. We apply the activation function. Then for forward, we give input data. We calculate the set. This can be moved. Just to make it a bit cleaner. Set equals cell.calculate set input data. Perfect. Then return result from the activation function. Okay, that's right. We could add an abstract for the layers, since they all seem to have the forward class. That would be nice, just as a good practice. So, oh, how did you write it? Class layer abstract A B C. Okay, so I have to import this from that one. Forward pass. Just call it forward. It takes inputs pass. Is this correct? Okay, this is not defined, which is important from that one. Okay. So we have an abstract class which requires that we have forward function that takes an input. Let's call it X. X is good. Forward, we rename input to just X. So the reason I'm changing this from, for instance, input to X is just to easily be able to like connect this to the mathematics. It's easier to refer to X than input, for instance, since when doing it on paper, you just call it X, and bias just B, you know. So now that we have this abstract class, we need to apply it. Okay. Do we just add it like that? Like this? I'm not sure about this. No. Can I create a consistent method resolution order MRO for basis layer? Wait, what? Wait, what? What's going on here? Can I create a consistent method resolution order? If anyone know how to solve this, please let me know. Else I'll just continue seeing what Copilot suggests. Can I create a consistent method resolution order MRO? Execution order. Wait, execution order? Oh my god. Yeah, execution order. We'll just swap these. Okay, so abstracts first before we extend. Plop, 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 plop. Yes, it's still working. Okay, let's close that empty file. So now we have the forward propagation working. Wow. So if we had proper weights and biases now, we could predict stuff, but that's the next step. We gotta solve that somehow. So let's take a look at that. How we go about doing that. So backward propagation for training the model. So here we have math for the forward propagation, which is not what we're looking for now. Oh, by the way, I saw that someone else joined the chat, so welcome. I hope you're having a nice day. I have one more monitor here where I'm looking for a file. Hold on. Just okay, yeah. Where is my file? I saw it. Wait, so backward propagation. Could be this file. Okay. Let's explore this one. See what we got. So here we talk about this is the image I had on Paint. So here we do the forward propagation where we actually apply all the math to predict, but we also need to do the backward propagation when we adjust it. You know, right now it's just a bunch of random numbers. It doesn't mean shit as it is right now. It's just weird. Example. Blah blah, multi-class classification. That would be fun to extend this this code so we can handle classification later. But right now it's just a regression problem, meaning we're just looking for number. Okay, multi-class, playground. Okay, so this is the wrong file. Let me check the other one. It's this one then. I guess it's treason then. Maybe not. Activation functions. Yeah, here we have more activation functions. Here we have the famous sigmoid function. We also have the town function and reload function. That's the one we're using. So this isn't of interest right now. I think this is a math for the oh, that's a softmax. So this is for classification. You see this math. So basically this if we have 4 potential classes, then they would all have a value between 0 and 1, where it represents in like a percentage how sure it is upon that specific class. So let's say it can only classify zeros and ones. Then would be, for instance, 82% sure it's a 1 and 18% is a 0. But that's for later. Gradient descent, here we have it. Here we have it. Okay. Ah, gotta stretch my legs and charge the phone. Okay, computation graph, blah blah. Yeah, when I did this by hand, pen and paper, it was confusing. Oh, I gotta eat some of my apple. I hope you can survive without my voice for a few minutes while I eat my apple and just scroll through this. But if you see anything interesting, let me know in the chat. I'm back. So wait, L. I think this was the L was the activation function, if I'm not wrong. No, not. Yeah, it is like. Wait, is it the activation function? What did L symbolize? I didn't know. L. Well, I would love to know, but I don't know. Oh, it's the loss. L is loss, I think. Scroll up, or is J loss? Cost function, sorry, cost function. And the cost function is that L is... You know what, I think I have the answers I'm seeking. Somewhere here. Perhaps it's this one. No. Yes. Maybe. Let's download this and explore. So just base calculations. Might have something. Yeah. Okay. You know what? I should have written more comments when I did this math, because I'm not sure what's going on here. Let's close that one down. Open up new window. Okay. Backward propagation math. It should show me something. Back prop is way of computing the partial derivative of loss function with respect to the parameters of a network. We use these derivatives in gradient descent exactly the way we did with linear regression and logistic regression. Okay. Medium. You can always trust medium.com. They have good stuff. How does learning occur in neural network? Yeah. Here we have the algorithm. Let's see if it's okay. Okay, so we use gradient descent algorithm. Yes. So gradient descent algorithm, by the way. So basically we are trying to minimize the cost function, and we do that by finding weights and biases that lets us get as far down as possible in one of these cavities. And this is just a 2D version, but if we look here, we have, for instance, a 3D version. But take into consideration that this is only 3 dimensional, which means it's 3 attributes that each data have, each like data row. But in reality, it might be like 20 or 40. But this is just symbolized. Here you see clear. It's trying to find its way to the lowest point. be a lot of reading. Propagation, the loss function. So we're also gonna have to decide for a loss function. We could go for the mean square error. I think that's a good one for our cause. Okay, so basically when you update a weight, you take the old weight minus the learning rate times the gradient. So we know how to find the old weight. The learning rate is set by us, but the gradient is what we're trying to find. And the gradient is the partial derivative of the loss function with respect to the bias. Okay. You will see a good example of the learning rate, by the way. So the higher the learning rate, the larger steps it takes. But that also means that it might take a too large step and actually get a worse result. As you can see, sometimes it's like suddenly further up. So when you train your model, you have to select good learning rates and sometimes even change the learning rate. You can often start with a high learning rate, then decrease that as time goes on. Okay, calculating the gradient. Let's consider this neural network with only one single neuron. Okay. So the layer number, we have the pre-activation function, the activation function, pre-activation function. I'm not sure what that is. Oh, this is the pre-activation function. Yeah, it's just normal calculation. Okay, so they ignored the bias. So calculated y hat, the output. Okay, so I think first thing we need to do now is to calculate the mean square error. How will we do that? Mean square error. Oh. Let's see. So take the true values, the predicted values, power 2. Yeah, that's correct. I think. We're gonna double check that. Mean square error. Yeah. So true minus predicted. Yeah. To the power 2, we sum it up, and we're also gonna divide it. What is Oh, yeah. So this should also be able to be written as divided by the amount of inputted data. Let's rewrite this without NP mean. It should divide by the length of y true or y pred. Yes, it did. Okay, but we're going to keep it like this because it's cleaner. So I have the loss function. You know what? Let's loss functions. Or should we place it elsewhere? Let's go to activation function. Static method. I'm gonna rename this to okay, should we just call it static methods or helpers? Oh, static methods. Okay, so we have the loss function. Okay. So backward. I'm not sure what to call it. Should we? Let's just train on all the data first. Or data set. Let's see. So it suggests that we take all the data, so data set X, data set Y. We take the model, number of epochs, and learning rate. Sure. And then we, for each epoch, we run once. Okay, so we run through all the data a certain amount of times for each epoch. So the for pass, this is what we're gonna be coding. Okay, so DC DV, so derivative V of C. This value basically tells us how any change in a weight affects the loss. Okay. The tree below shows how each term depends on other terms in the network above. Okay, so C depends on Y. So C, that's a cost. We have to remember that. Okay, sorry, I had to adjust how I was sitting. AL depends on Y. ZL, yes. So if we follow this image, let's see. I was thinking about drawing something similar for our specific case. Okay. Can borrow you. So first we have our basic input X. We have the first weights, the first bias. That gives us Z1. And Z1 leads to A1, which is the input for Z2, which also uses weights 2, bias 2. So you scroll up, that will give us A2, which depends on weight. Oh, sorry, I was wrong. Which is input to Z3, which also relies on W3 and B3. That will lead to A3 into our cost function, which is mean square error in this case, and Y. And Y, that's true label. So this is the predicted label, this is true label. This is a bit longer, but the method should still be the same. And we can see a clear pattern here. If we mark these, oof, yeah, 1. We have 2. We have 3. These are all the same, but the last one is a bit different. It's since it's the cost function, we're not following the same algorithm anymore. Okay. So we know that much now. Let's bring up this again. As you can see, the pre-activation function depends on the input, weights, and bias. The activation function depends on the pre-activation function. The loss depends on the activation function and the true labels. They forgot to mention that. The one top ground truth. Yes. So when we play the chain rule, we get this. So C. Okay. So how is C affected by? How is the cost affected by the weights? So first, cost is affected by the activation function's result. The activation function's result is based on Z. Oh my god, this is a great explanation. And this, the pre-activation result is based on the weights. Yes. This is something we can see in this presentation as well. See the math here. Okay, so we look at, so this is our loss function. How is it affected by V, by the weights? Why? Wait, why did we multiply by? Okay, let's. I don't know. This is confusing. Okay. So that one is affected by A. Yes. Here we have that. This is a... What function is this? Yeah, that was not it. That was something else. I think this will... No, we don't want to find the inverse. Okay, so the derivative of L based on A is that. Okay. Then pass it forward, so I said. So I calculate this one times the derivative of G. That's that. Okay. And then... Okay, yeah, so here we do it, here's for the weight and here's for the bias. Oh, wow, sorry. This lo-fi is making me too relaxed, falling asleep. We have now a phrase refer to this gradient. This instantaneous rate of change. Let's respect the weights. Okay. Well, what the fuck? Oh my god. I was afraid it would come to this. Okay. I can do this. Okay. So, let us extrapolate this knowledge gained from the gradient calculation. Okay, so this is for one input layer, two hidden layers, and one output layer. That's what we have. Yeah, that's what we have. Okay. So let's analyze this picture then. So we have the output here. We have the activation function, pre-activation function. That's and that's affected on the weights. For wait. Okay, wait. Oh my god. I'm not sure how to interpret this picture yet. It's too much. Okay, so this is the first set of weights. 1, 2, 2. Yeah, okay, so here we're talking about a 2x2 matrix. Meaning here we should have a 2x3? Oh, 3x2 matrix in this area. Here a 3x3 matrix. Okay. So let's focus on this. You know, let's take a picture of this instead of move it to paint. Okay, so I've done this math before, but for way smaller neural networks. Even this one's tiny, but even simpler. But I feel like I can't just apply that knowledge instantly. I have to do step by step, like really learn it basically. Okay, we'll insert this here into our beautiful paint. Okay, so here we have one weight matrix. Here we have one more. Wait, we have 4. Why do I have 4 weight matrices? Let's should we print out all the weight matrices to see what we can find out about them? Model, layers, 0, weights. Yeah, it doesn't have any weights. Wait. Something wrong then? Let's just move forward. Let's forget we found something might be wrong. It's not wrong, it's correct. It is as it should be. See, so we let's zoom in here. And I need to draw. I don't know why, but I need to draw. So this one, let's say third layer. Okay, so this is layer 1. Layer 2, layer 3, layer 4. And this is affected by these. 2. Yeah, it's that one's. Those are connected to that one. That makes sense. But why are they coming? Yeah. Okay. So basically, Z4 is affected by weight 4, which here are all these 3. And these 3 are affected by these. Wait, no, they're not affected by them, but they are multiplied by these values sent from these. Okay. It's one step in the right direction. Okay, I gotta take a 5-minute break. I will be right back. Okay, I'm back. Let's get back to it. So we work on the backward propagation. I'm not sure how to handle it right now, but let's scroll a bit further down. So the pre-activation function of each of these neurons is given by the pre-activation of each of these neurons set is given by J7 same 1 Okay, yeah, we have all of them times. Yeah, okay, yeah. This makes sense, I guess. This makes sense. Here the gradient is given by Hej, hur mår du? Eller ja, Olivia, hur mår du? Mår du bra? Du kanske kan ha i den här chatten när du är redo. Eller ni är redo att spela. Oh no, du måste fixa ryggen. När ska du till när ska du till läkaren med det? Jag vet inte vad som har sagt. Men vi vibe. Vadå vi vibe? Du är så redo. Woo! Nice. Jag är inte. Alla borde ändå alltid stå på spel ändå. It is the way. Du borde ha en fake yxa som du kan ta tag i när du laddar för att göra någonting spel. Ska bara hålla upp den och skrika. Det vore perfekt. Så jag sitter lite fast just nu. Ja, true. I alla fall, jag försöker lösa backward propagation för att träna ett neural network. Oh! Det blir höstdatum 8%. Ja. Okej. Nice. Men vänta, hallå, vänta. Så du ska operera i höst. Det är fantastiskt. Hoppas det blir tidigare. Det hade varit nice om du kunde göra det liksom typ nu över sommaren, men kanske inte, kanske svårt, jag vet inte. Och det jag gör är this neural network. Okej, så jag kodade neural network från grunden med Python. Och än så länge så har jag inte kommit superlångt. Jag har byggt for propagation. Så basically man kan bygga ett nätverk, neural network med olika lager. Du har input layers, output layers, hidden layers. Och du kan bygga modellen och de kan ansluta till varann. Och infektionsrisker. Ingen minns fegis. Anyway, jag har byggt en modell som kan predikta saker, men nu måste jag göra så den kan tränas också. Matten där är helt fucked. Jag tänker för att hantera infektionsriskerna kan du inte bara köra som Trump sa man skulle göra, typ andas in handsprit. Trump breathe du kan nej hand Sanitizer. Jag vet inte hur man stavar det. Ah, yes. Ah. Amazing. Ja, men alltså varför inte klor liksom? Det är starkt. Det slår även ut lite andra saker. Lite annat shit. Det är liksom... Så tar det som nässpray. Han är vis, Olivia. Han har förståelse bortom oss. Det är det handlar om. Det är vi som är dumma. Han är smart. Okej. Lycka till med maten. Okej, så kanske lite greedy. Okay, easily calculate the gradient. The output node if you know the values of the following terms. Derivative of the error. I don't know. I don't want to just look up how to do it in Python directly. It's more fun to understand it. So those are the weights. So when we do the backward propagation, which order do we adjust the weights and biases? Multiple layers. Oh, we update all the layers simultaneously. So we know this much, but wait, okay, do we update all the values in the weights? Because here they... This is a vector, or is it a matrix? Let's say, it's a matrix, I think. Or is it a weight? Vector. Yeah, it's a vector. And that means that we subtract. Do we subtract the same value from each weight, the weight matrix? Equation 1. Assign to blah blah blah. So we can updating organisms simultaneously. Okay. So update everything simultaneously, like update it. Okay. In principle, you could update each parameter bar individually. To be more precise, you would have the following update rule. Okay. Okay. So let's go to the code file. Hey. Hey, Gia. Okay. Ah, sad note. Okay. So we need to find the graded descent for the for the cost function. How do we do that with Python though? Let's keep that. Check this out. Okay. This is Swedish. Let's go back to English. Better. You can do this. Yes, I can. Hopefully, in a few hours or so. My best guess is that I'm gonna complete this tomorrow, but it's very fun. It's super fun. Okay, so let's see. So I'm trying to find some inspirational code for how to find the derivative we're looking for. Wait, why did I use num? Square error. Yeah, this is better. I was thinking we could use just the POW built-in POW function in Python, but that would look something like this, but it doesn't support matrices, so we will stick with NumPy. Okay, so I have mean square error. I have the same. Our task is to find the optimal value of weight W by B, which can fit our model well, but give very loss. Yeah, we want to minimize that, obviously. So we want to minimize the cost function. Cost function is it's a way of calculating how bad a AI model performed. So, for instance, so this can be a cost function. So we have this this line here. So we want to get as low as possible in it, and somehow we have to adjust our weights and biases. So basically, the settings of the neural network to achieve this. And here they're talking about learning rates. So learning rates is at what rate it adjusts itself. So too high learning rate means it will take too large steps and might miss the optimal settings. But too low might mean that it gets stuck in these local minimums. So we are trying to find the global minimum, but you can get stuck in local minimums if you're unlucky. So how the gradient descent works. Okay. Whoa. Oh, and this is big. Okay. So we find the derivative with respect to v. That's weights. Yes. Okay. Okay, so here we do the same thing for the bias, we do for the weight. So this math should be very similar. YP, Y2, because the difference is only the X. I think I saw something about that here. Yeah, look, they're the same, but it's just times the X. So that's something. So that connection. So B. Oh right, so the blue is just calculations, and figure out that the LD Z is A minus Y. All these ads. It's too many. Let's just remove them. Perfect, that one's gone. That one's gone. Oh my god, one more. Seriously? There we go. So I have a learning rate. Not plotting anything right now. Find the gradient. Okay, so you need to find the class, define. This is kind of cheating now. No, okay, no, I'm not gonna look at that, it's too much. Oh, God. So we call upon a function called backward. But Where's the backward function? Oh, welcome to the stream, by the way. So right now I'm working on a just basic neural network to solve a linear regression problem. I've done the forward propagation, now it's the backward propagation, that is basically training the neural network, and I need to find the gradient of the loss function. I'm trying to understand the whole picture of it and not just look up how other people done it. It's a pain in the ass. So I guess you should follow if you like to watch people suffer with code, because that was what I'm doing right now. But I love the suffering. Let's see if we can find the back function. Find the gradient using loss.backward. Wait, loss.backward. So I'm reading this guide now, and they're referring to a function called backward, but they never really tell you where they defined it. Yeah, so that's basically the gradient descent. Yeah. What do you suggest? Okay, so first, yeah, that's true. First, we need to predict some shit. We need our predictions. Let's call it pred. So we've done the forward pass. This time for backward pass. The error. That's not the error. The error should be should be static methods dot wait error method. Wait, what? No, it's the cost function, damn it. Okay. Error equals cost function. Yes. Okay, so let's print this out. Could be fun to see what happens. I will probably crash my computer, but fuck it. Alright, I need to call the function. Okay, so this should be inside the model class. This dot predict. Oh, self dot predict. Sorry, wrong language. What? What? Alright. Self learning rate. Yes, that's fine. Cost function. We could set the cost function. Self dot cost function. So we need a cost function. Dot cost function. There we go. Epochs. Learning rates. Yeah, we're not applying learning rate yet, but that's okay. Model dot fit Yes. Wait, that many epochs? Let's start with 10 epochs. Okay, okay, we have errors here that are freakishly large. This is bad. It's like 11,000, 4,000. Oh my god. It's funny. Okay. So we know that we do have some errors. So we have an error here, and what do we do? What do we do? I feel like I'm shrinking down on my chair. I should sit down more properly. Sit up more properly. What do you suggest? Self.backward. Okay, so Copilot suggests that we create a function called backward that would pass the label, the prediction, and the learning rate. That sounds about right. Backward, we're gonna give it these. Calculate the loss gradient. Yeah, this is what I want to do. So the loss gradient is a predicted minus true value. Wait. Okay, so basically here, if the true value, if predicted is 100, true is 90, then the loss is 10. And okay, so you go through the layers in reverse. If we go through the layers in reverse, we go from the last layer and calculate the gradient of the loss with respect to the output of the layer. Okay. So loss function, we go back. Okay, so layer doesn't have a backward method. Wait, so you know what? I have an idea. ChatGPT, let's go. It will probably not work. How? Okay, watch me crash this. Okay, so initialization, set learning rate, blah blah, yeah. Forward propagation, yeah, we've done that. Compute cost, yeah, we can compute the cost. Backward propagation, okay. Number of examples. Okay. So a minus a2 minus y. gradient of cost with respect to Z2. Okay, start from the right. B. Okay. Let's see what it suggests. We're gonna go up to layer, depth, backward. So we go through each layer. I lost myself here. Lost gradient, layer backward. Okay, I have to fix a quick thing. Hold on, like 2 minutes. Okay, let's do this. Okay, so when we fit the model, we're gonna do backward propagation. So start if I look at the loss gradient. So that's loss gradient for like the cost function, and that is. Loss gradient. So this is trickier than I thought it would be. So we have the cost function. We need to find the gradient of it. This one suggested okay. So Copilot suggests that we calculate the gradient of the weight and bias. Yes. The gradient of the weights is a dot product of the gradient of the weights is dot product of the loss gradient and the inputs. Gradient of the weights is dot product of the loss gradient. The gradient of the bias is a loss gradient. Let's see, let's read this. So weights gradient, numpy dot product of loss gradient self inputs. Wait, what do you mean self inputs? Okay, so it's supposed to store the inputs. So I need to store the inputs. Say for gradient descent. Bias gradient. Loss gradient. I guess that makes sense. We update the weights and bias using the gradient. So weight, we subtract learning rate times weight gradient, and we just bias by that. Return the loss gradient for the next layer. Okay, so it takes layer by layer, from right to left. Okay. That should be it. Okay. T. Let's go back up. Wait, what? So weight gradient, loss gradient, self T. Okay, let's go there again. Okay, okay. So, what do we have? So the last is only one value, right? Wait, what? I'm trying to do the dot product here. But how can you do the dot product when there's a single value? Well, folks, I think it's time to end this stream now. I'm done for today. My head is boiling. So, thank you so much for watching and have a great evening.